Hello everyone, I am Dr. Rajesh and I welcome you in this video lecture. And in this video lecture we will solve these four problems based on Leibnitz theorem. So we will be solving these problems. So let us name these problems as this is question number 1, this is 2, this is 3 and this is 4. So we will be solving all of them. So let us take the first problem first. This is the given and we have to show by Leibniz theorem that 8th order derivative is equal to 28 d square y by dx square minus 48 dy by dx plus 21 y. So since we are given that y is equal to x square e raised to the power x. So this is given and we have to prove that d square y by d8 y by dx8 is equal to this quantity. So we have no option but to apply the Leibniz theorem and find its nth order derivative. Now recall the Leibniz theorem. What does the Leibniz theorem states that? It states that the nth order derivative of the product of two functions is given by nc naught, nth order derivative of u v naught plus nc1 u n minus 1 v1 plus nc2 u n minus 2 v2 plus and so on n cn u naught vn. So that this is by Leibniz theorem. Now we will be applying Leibniz theorem upon this one. So among x square e raised to power x, which quantity is to be assumed as u? Here you see in this formula that we have written over here, nth order derivative of u is existing. So among these two, e raised to the power x is the only quantity whose nth order derivative exists and it is equal to e raised to power x as such. So this will be assumed as u and this has derivative only up to second order. Its third order derivative will be 0. So this will be assumed as v. So I am going to write it as, this is assumed as u and this is assumed as v. So now applying Leibniz theorem we will get applying Leibniz theorem. Leibniz theorem we get, now what will get yn, this will be yn and now apply Leibniz theorem, it will be nc naught nth order derivative of u over here is e raised to the power x nth order derivative, x square 0 order derivative same function as such plus nc1 n minus 1th order derivative subscript n minus 1 x square first order derivative plus nc2 n minus 2 order derivative x square 2 and third order derivative will be 0 because here its third order will be 0. So the following terms will become 0. So I will be writing here 0. Fine. So we know that nth order derivative of e raised to the power x is same, n minus 1th order derivative is also same and n minus 2 order derivative is also same in case of e raised to the power x. So, here I will be substituting nth order, n minus 1th order and n minus 2 order, and first order 0 order derivative of x square will be x square, first order derivative will be 2x, and second order will be 2. Okay, it will be 2. So, what will it become? It will become nc naught, you know, is 1. Okay, so this will be 1 into e raised to the power x into x square, fine, plus n e raised to the power x, it is 2x, plus n minus 1 by 2 e raised to the power x dot 2, because we know second order derivative of x square will be 2. Here I can write it down. If you, it is v na, v is equal to x square, fine. First order derivative will be 2x, second order derivative will be 2, and the same thing is substituted here. This is second order, okay, this is first order, and this one is 0 order. Okay, so these things have been substituted. Now cancel whichever is cancelling, this 2 to 2 will cancel out, and now take the common e raised to the power x as common. So what will get? E raised to the power x is common, fine. It will be x square plus 2 nx plus n minus 1. Okay, so this you will get. Now this will be yn. Okay, and we have to find, look, we have to prove that this thing we have to prove. We require y8, y2, y1. Okay, so we will be calculating y8, y2. So I will be calculating. So put n is equal to 8 to calculate y8, fine, because we will be requiring to prove. So this y8 will be e raised to the power x, x square, n is equal to 8, 16, n is equal to 8, 8 into 7 is 56. So I am going to write it is plus 16x plus 56. So this equation will be named as equation number 1. Now put n is equal to 2 in, say this equation is a, put 2 in a and here in a also, fine. So y2 will be e raised to the power x, x square, when you will put 2 into 2 is 4, so this will be 4x plus, here if you put 2 minus 1 is 1, 2 into 2 2 into 1 is 2, so this will be 2. So this is y2, and y is of course given as this quantity is y, x square e raised to power x. Now we have to prove the result, which is I am writing again, y 8 is equal to 28 y2 minus 48 y1. We also need to calculate y1. Okay, so we will be calculating it, 21y. So you can look it from here. 28 d square y by dx square minus 48 y1 plus 21y. So we also need to calculate y1. So I will be calculating. So to calculate y1, put n is equal to 1 in A. So here you will put n is equal to 1. So this will be 1 minus 1 will be 0. So this will be y1 is equal to e raised to the power x square plus 2x. Fine. And you can name this equation as 2, this equation as 4. So equation left hand side is, of course, this equation number 1 is left hand side. Now we will be working upon right hand side, and we will try to prove, we will try to establish that right hand side is also equal to y8. So 28 y2 minus 48 y1 plus 21 y. This 28, what is the value of y2? You see over here, this is y2, okay, and this is y1. So I am going to put it over here. 28 e raised to the power x square plus 4x plus 2 minus 48. What is y1? E raised to the power x square plus 2x plus 21. Y is x square e raised to the power x. Y is x square e raised to the power x. E raised to the power x will go outside, okay, it will be common, is out, okay. This 28 will multiply inside, and it will become 28 x square plus, it will be 1 12 2 x plus 56, okay. This will multiply 2, this is 56, and this will also multiply, minus 48 will multiply, it will be minus 48 x square minus 96 x plus 21 x square. Fine. So this is the case, okay. Now we will collect the coefficient of x square, okay. It will be 49 and 48 gone, it will be x square e raised to the power x is equal to x square, and here you see 112 minus 96 is 16x, okay, and this constant term is the alone term. So this will be plus 56, okay, and here if you pay attention, this is nothing but y8, this is same. So this is equal to y8, which is nothing but left hand side. So therefore we have proved the result. So here you will write, we have proved the result. Now we will be taking up the next problem, and in the next problem we are given that, look at here, this is the second problem, x is equal to sine log y by a, and you have to prove this thing. So this thing is given, so I will be solving the second problem, and we have to prove this thing. So let us see what happens. I am solving the question number 2. This is question number 2. We are given that this is x is equal to sine log y by a, and we are required to prove 1 minus x square y n plus 2 minus 2 n plus 1 x y n plus 1 minus n square plus a square y n is equal to 0. This is required to prove. Now, this sign will go over here, it will make sine inverse x is equal to log y by a. So, it is equivalent to applying the sine inverse function on both sides. This will cancel out and it will become identity. So, this a will go over there. This implies that a sine inverse x log y. Now, raising exponential on both sides, we get e a sine inverse x is equal to y. So, this implies that we are given the question in this form, and this question we have already solved many times. So, if you insist, I could solve it again, but we have done it many times. I could solve if you insist. So, this question you have to prove this one. So, let me handle this one. So, we have no formula for exponential. So, what we will be doing? We will be differentiating it first with respect to x. Okay, now differentiate it with respect to x. What will get? Write it over here, differentiating both sides with respect to x, we get, yes, what will be getting? It will be y1 is equal to e raised to the power a sine inverse x as such into a is a constant quantity, differentiation of sine inverse x will be a is as such, differentiation of sine inverse x will be root 1 minus x square. So, this implies that so if you see, this thing is nothing but a y. So, I am going to put it over here. So, our first priority is to get rid of this square root, because it is going to cause many complication, and if this square root will remain here, you will have to use the quotient formula. So, we are also trying to avoid that condition in which we have to use the quotient formula. So, here instead of quotient formula, we will be using the product rule by multiplying it over there. Fine. This implies that y1 root 1 minus x square is equal to ay. Now, squaring both sides, we get y1 square 1 minus x square is equal to a square y square. Now, we have to differentiate again, but here we are given two functions in product and both are a function of x. So, one will be x, one will be u and one other will be v. So, we will be using the product rule. So, I will be assuming one function as u, other as v. So, I am again going to differentiating again with respect to x. What will be getting? You will be getting differentiation of y1 will be 2y1 y2, fine, and 1 minus x square as such. Now plus sign y1 square, differentiation of 1 minus x square, it will be minus 2x is equal to a square into 2y y1. Differentiation of y square is 2 will come here, y it will become y raised to power 2 minus 1 will y, and differentiation of y will be y1. So this is 2y y1. Now both sides we are cancelling 2y1. So what will be getting? This 2y1 will go from here, 2y1 it is y square, so 1 will remain, 2y1 will go from here, so it will be y2 1 minus x square minus x y1 is equal to a square y. This implies that y2 1 minus x square minus x y1 minus a square y equal to 0. So this we have obtained. Fine. Now we have to prove the result, and for the same we have to, because the result which is required to prove in that yn plus 2 is involving, so we have to differentiate it successively n times with respect to x. So here will be Leibniz theorem will be applied because it is product of two function here also. So let us see applying, or you write differentiating successively n times with respect to x. So you assume over here this is having nth order derivative, this is u and this will be v. This is having nth order derivative, so this will be u and this will be v. This is u and this is v. Okay. Now applying the Leibniz theorem, what will get? So this will be solved here. So I am applying the Leibniz theorem over this one first, then this one. So you will see nc naught y2 nth order derivative, 0 order derivative of 1 minus x square plus nc1 y2 n minus 1th order derivative 1 minus x square 1 plus nc2 y2 n minus 2 1 minus x square second order and derivative. So and this will also we will be applying Leibniz theorem on this one. This will be minus nc naught, and what is that? This is nth order derivative, this is u. Okay, so this is y1 n 0 order derivative of x plus nc1 into y1 n minus 1 into first order derivative of this one minus a square y, it will be minus a square yn equal to 0. This implies that nc naught is 1, this will be y n plus 2 1 minus x square, nc1 is n, y2 n minus 1 is equal to y 2 plus n minus 1 is equal to y n plus 1. So, this will be y n plus 1 into minus 2x plus n minus 1 by 2 yn, and second order derivative of 1 minus x square is minus 2, and this y2, this is y2 n minus 2 is equal to y 2 plus n minus 2. This will cancel out, this is yn, and this is minus 2 minus nc naught is 1 yn plus 1 into x plus n, this will be yn, and first order derivative is 1 minus a square yn equal to 0. Now we will collect the likewise term yn plus 1, yn plus 1, yn, yn, yn. We will be collecting them. Before that, cancel it out. 2 to 2 will cancel out. So, this implies that 1 minus x square, this is single term, minus 2nx yn plus 1 minus n minus 1 yn minus yn plus 1 x plus nyn minus a square yn equal to 0. So, collect the terms containing yn plus 1 and yn. This will be minus 2n plus 1 x yn plus 1. Okay, from here minus is common, x yn plus 1 is common, x yn plus 1 is common, minus is here. So, this is what we get. Now, here minus is common. So, n minus 1 as such, minus is common plus n, minus is common plus a square. So, this will be n minus 1 plus n plus a square yn equal to 0. This implies that 1 minus x square yn plus 2 minus 2n plus 1 x yn plus 1 minus n square minus n plus a square yn equal to 0. This implies that 1 minus x square yn plus 2 minus 2n plus 1 x yn plus 1 minus a square plus n square yn equal to 0. So, this is the result that we are required to prove. Now, we are left with the next problem, and next problem is, so I will be giving you the hint and you will be doing it at your own. This is the problem and we have to prove the result. So, how will you do? Let me show you how will you do it. This is question number 3. We are given that cos inverse y by b is equal to log x by n raised to the power n. Okay, and we are required to prove the recursive relation containing n plus 2 derivative. Now take this one over there, what will get? Y by b is equal to cos log x by n, and this n will come before this one, so this will be n log x by n. This implies that y is equal to b cos n log x by n. Okay, now you have to differentiate it because we don't have the formula for cos in which its argument is log, and we don't have any formula. So we will be differentiating with respect to x. So what will get? Minus b sin n log x by n into n. This cos is done. Now n is constant. Log x by n differentiation will be x by n. So here I am going to write x by n. Now this log is done, x by n is left, so differentiation of x by n is 1 by n. So this will cancel out and this will go over here. So this will be minus nb sin n log x by n divided by x y1. This implies that x y1 is equal to minus nb sin n log x by n. Now do one thing. This is the product of two functions. This will be u, this will be v. We will be using the product rule to differentiate again. So we have no option and name this equation as equation number 1. Differentiate again with respect to x. What will get? X as such differentiation of y1 is y2. Now y1 as such differentiation of x is 1. It is 1. Fine. Is equal to minus nb sin differentiation is cos n log x by n. Okay, fine. So this is done. Now sin is done. Differentiation of n and log is x by n and 1 by similarly last time that we did. Fine. So this will be, this will go up, this will be n square. This is equal to minus n square b cos n log x by n. Fine. Divided by x. So this will go and multiply with this one. So we are having x square y2 plus x y1 is equal to minus n square b cos n log x by n. Now from this equation, say equation number 2, this thing b cos n log x by n is nothing but y. This is equal to minus n square y. This implies that x square y2 plus x y1 plus n square y equal to 0. Now you have to apply the Leibnitz theorem upon this one. So now I am going to apply the Leibnitz theorem and differentiate 3 successively n times with respect to n. What will get? And you know nth order possible of this one. This is u, this is v, this is u, this is v. Okay, so this will be n c naught nth order derivative of y2 x square naught plus nc1 y2 n minus 1 first order derivative, it will go in increasing nc2 y2 n minus 2 x square 2, and after 2 it is not possible. So nc naught, because after 2 x square will become 0. This will be, here we are applying, this will be y1 n x0 plus nc1 y1 n minus 1 into x1 plus n square yn equal to 0. This implies that nc naught is 1 and y2 and y2 differentiating n more times, this will be n plus 2, and x0 order is x square as such. N, this will be yn plus 1, first order of x square is 2x, n minus 1 by 2, it is yn into 2 plus nc naught is 1 yn plus 1 into x plus n into yn, first order is 1 plus n square yn equal to 0. 2 to 2 will cancel out. This implies that x square yn plus 2 plus, now collect yn plus 1 and yn plus 1. This will be 2 n plus 1 x yn plus 1 plus yn is common, this will be n square minus n, this will be plus n plus n square equal to 0. This will cancel out. So we will get x square yn plus 2 plus 2n plus 1 x yn plus 1 plus 2n square yn equal to 0. This was required to prove. So this is the solution of third problem. Now we will study the fourth one, and in the fourth one I will give you the hint and will find this up to this relation only, and leave up to you to apply the Leibnitz theorem and find the result. So what is the third problem? Let us see. Here is the third problem. We are given this one and we have to prove this thing. Okay, so we will be doing it. So let's do it. This is question number 4th, not third, it is question number 4th. If y is equal to sine inverse x by root 1 minus x square, then we have to prove. Now differentiate, first time apply the quotient rule, root 1 minus x square whole square root 1 minus x square as such, differentiation of sine inverse x, which is 1 minus x square, minus sine inverse x as such, differentiation of root 1 minus x square, this will be 1 by 2 root 1 minus x square into minus 2x. This 2 to 2 will cancel out, this will, so now this will be 1, and this minus minus will become positive. So this will be plus x sine inverse x divided by root 1 minus x square divided by whole divided by this square to square root will cancel out. So we are left with 1 minus x square. So this is further equal to 1 plus x, and this sine inverse x by root 1 minus x square will become y. So this will be xy divided by 1 minus x square. So now this will multiply over here. This implies that 1 minus x square y1 is equal to 1 plus xy. Now differentiate again with respect to x, we get. So what will be getting? Differentiating again, it will be 1 minus x square y2 plus y1 as such. 1 minus x square, first differentiation will be minus 2x. Differentiation of 1 will be 0. Apply the product rule. Differentiation x will be 1, y, x as such. Differentiation y is y1. 1 minus x square y2 minus 2x y1. This is y plus x y1. So 1 minus x square y2, this will come over here, minus 3x y1 minus y equal to 0. Now apply the Leibnitz rule quickly. This is u, this is v, this is u, this is v. We have done many times. So what will get? nc naught y2 n 1 minus x square naught plus nc1 y2 n minus 1 1 minus x square 1 plus nc2 y2 n minus 2 1 minus x square 2 minus 3 nc naught. This will be y1 n x naught plus nc1 y1 n minus 1 x 1 minus yn equal to 0. Now we write it further. Substitute the various values. Yn plus 2 1 minus x square plus n yn plus 1 into minus 2x plus n minus 1 by 2 into yn into minus 2 minus 3 1 yn plus 1 into x plus n into yn. Differentiation of x with respect to x will be 1 minus yn equal to 0. So this will be 1 minus x square yn plus 2 minus 2 nx yn plus 1. This 2 to 2 will cancel out, minus n minus 1 yn minus 3 x yn plus 1. It will be minus 3n yn minus yn equal to 0. So collecting the corresponding terms, yn plus 2 minus 2n plus 3 x yn plus 1 minus yn. This will be n square minus n. It will be minus is common plus 3n plus 1 equal to 0. This implies that 1 minus x square y n plus 2 minus 2n plus 3 x yn plus 1 minus yn, this will be n square plus 2n plus 1 equal to 0. This implies that 1 minus x square y n plus 2 minus 2n plus 3 x yn plus 1 minus yn, this is nothing but n plus 1 whole square equal to 0. So this was required to prove. So in this lecture we have studied 4 problems based upon Leibnitz theorem. So these 4 problems are very important from examination point of view, and we have studied all these problems, and this sums up the application of Leibniz theorem to find the product of two functions. Next we will find, in the next lecture we will learn to find y n 0 also from here. In these formulae we have to establish these relation also. Along with this we will try to find in the next exercise y n 0. So that's all I have from this lecture, and if you like the lecture, please like, subscribe, share and comment. This is Dr. Rajesh saying goodbye, take care, bye bye, and see you soon.